A magnitude 9.0 earthquake isn't just a little bit stronger than a magnitude 7.0. A magnitude 9.0 earthquake releases 1,000 times more energy than a magnitude 7.0. It is the energy equivalent of 32,000 atomic bombs detonating at once. When a force this massive hits a structure this tall, intuition tells us it should snap like a dry twig. And for most of human history, it would have. But today, in cities like Tokyo and Santiago, skyscrapers ride out these massive quakes and barely spill a drop of coffee. How are these skyscrapers able to ride out these massive quakes? They don't try to be strong, they try to be tricky. To understand the solution, we have to understand the enemy, inertia. When the ground moves, the building foundation moves with it. But the roof, 400 meters up, has a mass. It wants to stay where it is. This lag creates a massive shear force. The bottom goes one way, the top stays put, and the middle is torn apart. But there is a second deadlier force, resonance. Every object has a natural frequency at which it likes to vibrate. Low-rise buildings vibrate fast, about 0.1 seconds per cycle. Skyscrapers are slow, majestic beasts. They sway back and forth once every 4 to 8 seconds. If a distant, massive earthquake generates long-period waves that match the building's natural rhythm, the sway amplifies. This is resonance. The building acts like a tuning fork. If we don't stop it, the swaying becomes so extreme that the structural columns can no longer hold the vertical load. So, how do we stop it? The first line of defense is ductility. Think of a paper clip. You can bend it back and forth many times before it snaps. This is ductility, the ability to deform without breaking. Engineers design specific parts of the building to act as fuses. We want these beams to get damaged. Every time a steel beam bends or a concrete core cracks, it burns off the earthquake energy. It is better to have a cracked beam than a collapsed tower. But relying on damage is a last resort. Modern engineers prefer to cheat the physics entirely using two massive technologies. First, base isolation. Instead of placing the building directly on a foundation, we place it on a massive rubber box like base isolation, reinforced with steel and lead. It acts like the suspension in your car. When the ground shakes, the building remains standing. But for super tall skyscrapers, base isolation is often too unstable. So we use a giant pendulum. This is a two-mass damper. It is essentially a counterweight. When the wind or an earthquake pushes the tower to the right, the ball lags behind and swings left. It pulls the building back against the sway. It creates a damping force that kills the resonance before it can destroy the structure. So, can a 100-story building survive a 9.0 earthquake? The answer is yes. Not by standing still, but by moving. By accepting the energy, processing it through rubber, steel, and physics, and dissipating it safely.